Okay, electric fields. They're an interesting concept. You're very familiar with the gravitational field, but we don't really call it that. We just say, oh, there's gravity, and gravity's due to the Earth. And if you tell me the mass of the Earth and the radius of the Earth, I'll tell you the gravitational field of the Earth. And if you tell me your mass, then I'll tell you the force of that field. I'm going to tell you the force of the Earth's gravitational attraction between you and their mass. So electric fields are the same way. They're very connected to force, but they have a lot of advantages to talking about the force on an object rather than the field from an object. So an electric field is given by the formula, and it ties exactly into what we were doing before. KQ over R squared, where K is Coulomb's constant of 9 times 10 to the 9th. And again, I just want to remind you that the electric force was K, some Q1, and some other charge Q2, R squared. And again, it's a vector, and so is an electric field. And I guess it's the same thing for gravity. There's a lot of comparisons here. When we start talking about the gravitational force, G, M, two different masses, and the distance between the masses, and this is some attractive force of gravity between two masses, and capital G, universal gravitational constant, is some proportional thing, just like Coulomb is here, and this is force. It's in newtons, right? Both of these things are in newtons. But we want to measure, just like we want to measure the gravitational field. Well, what's the gravitational field? Well, you don't think of it as the field, but we certainly know what little g is, right? Little g is 9.8 meters per second squared, and it tells us what happens when we put any mass, doesn't matter what the mass is, any mass we can put in Earth's gravitational field. Again, this is Earth. Little g is obvious, hopefully it's obvious that it's different on the moon than it is on Mars and so on. But Earth's gravitational field is 9.8 meters per second because Earth's mass, based on g and based on Earth's radius, creates a certain field. Well, that's what charges do too. If you put a charge, and this is only one charge, it creates a field around itself, an electric field, and it's telling you how many newtons per coulomb it would do. So if you take one charge, and let's just take a positive charge. All right, so there's my positive charge, and I'm saying just like the Earth, if you take the Earth and it's so massive, if you just tell me the mass of the Earth and the radius of the Earth, then I can predict the gravitational field around the Earth. I know that things will accelerate inward at 9.8 meters per second squared. Very similar here. If you tell me the charge here, I can tell you the electric field at any point in space. The electric field is a function of the charge, meaning how big this charge is, and then how far you are away from that charge. So if I wanted to know the electric field at that moment right there, I just need to know that the E field is KQ over R squared, where R is that distance. And in this case, we always draw fields with respect to what a positive test charge. Again, we're thinking about what's right here. We're thinking as if there's a positive test charge. In gravity, we don't have to worry about whether the falling mass is a positive or negative because they're always just an attractive force. But here, we're always looking at a positive test charge. And so what would that field do? Well, that field would go that direction. So at that moment, that would have some electric field, and it's going to be so big. So let's say that the electric field at that moment, we know it's pointed to the right, was, let's say, 20 newtons per coulomb, right? Those are the units for the electric field. And I could figure out what charge I need to put and how far I need to put it away to create an electric field of 20 newtons. So let's say that that charge at that moment creates a 20 newton per coulomb electric field. So what is that saying? That says that if I put a third charge there, Q3, that it will experience 20 newtons of force per coulomb of charge. So if this was 3 coulombs, then it would experience 60 newtons of force to the right. If it was 5 coulombs, then I would experience 100 newtons of force. So the electric field is telling you what would happen, how many newtons per coulomb at that space. an electric field, hopefully you're okay that it would go, if I had to redraw this picture, instead of looking just at one point in space, if you have to think about what a positive charge would do, what does the electric field do to that? Well, it goes spherically outward. And they would say that the number of lines coming out should be proportional to the size of the charge. And so we would draw arrows that way. Because if you came and you put a positive charge anywhere along this thing, what would happen? So if you put a positive charge there, what would happen? Well, it would experience a force upward. If you put a positive charge here, what would happen? Well, it would repel it that way. If you put a positive charge down here, it would repel it that way. If you put a positive charge here, it would repel it that way. And again, how big of a repulsion? Well, the force is just how many coulombs you put times 20 newtons per coulomb, or whatever the electric field is at that moment. But again, this single charge, one charge, just a Q, created an electric field. If you want to actually find a force on something, well, then you have to tell me what this additional charge is, and then I can tell you how big the force is. Hopefully you can combine these two formulas and say then the electric force is just QE, which I'm hoping at this point makes sense. One charge can create an E field, or an E field and a charge. Again, these are just off by a Q. Again, sometimes it's very advantageous for us to talk about the field created by a charge rather than the force on a charge, because I want to be able to put whatever charge I want wherever I want and be able to talk about what would happen to that charge. Again, so that's what a positive charge would look like. Well, what would a negative charge look like? Well, a negative charge still has E fields, but what would it do? Well, it's always just inward then. Because what would a negative do to a positive? And again, we always draw our E fields with respect to what would happen to a positive charge. If I put a positive charge here, what would it do? Well, it's going to go this way. And again, hopefully it makes sense that the electric force is always in the same direction as the electric field. You're always going, tangent to that thing. Okay, so let's draw some other electric fields. All right, we look at the electric field all the time. This one is classic. Go back to like a parallel plate capacitor, and we have something that looks like this. Our parallel plate capacitor has one plate is positive and one plate is negative. Okay, think about what would forget about that even existing right now. What would all of these positive charges do? Well, they're going to have an E field that goes straight across. What do the negatives do? Well, they also have that same E field. These guys are pushing, these guys are pulling, and the E field is this way. And the best part of a parallel plate is that the E field inside is actually uniform. And we use that big time. If you want a uniform E field, and a uniform E field then creates a uniform force, meaning the force is constant, and then a constant force then produces a constant acceleration, and then we can do all sorts of things like the V squared equation to find the velocity once this charge is accelerated over. And again, you only get a constant force if you have a constant E field. Otherwise, if you think about our point charge again, our point charge looked like this. Right, the E field was spherically outward. But the other thing, not only is it not really in a uniform direction, but the electric field is a function of R, kq over r squared. Right? This is another inverse square one. The electric field, if you double the distance, you cut the electric field into a quarter. Well, so an object, or a charged particle, if the little guy was here, and then once it got over here, well, the electric field isn't the same, so electric force isn't the same, so the acceleration isn't the same, and we can't do things like this. So having a parallel plate capacitor and having a uniform E field is pretty money here. Okay, and then a couple of videos in the future, we'll look at finding the electric field due to Gauss's law in a situation like that. But right now, you can just assume that we can create a uniform electric field between a parallel plate capacitor. We could look at a dipole. A dipole is like a positive charge and a negative charge. And what would the E field look like? Well, if you were right in between here, what would the E field look like? Well, this guy's pushing and this guy's pulling. That's the E field. And then if you looked there, what would happen? Well, see how this one would get pushed this way and this one would get pulled that way? And so it end up being that the electric field looks something like this. Okay, and it's always going this way. And if you wanted to know the electric field at any moment, the field is always tangent to the path. And so if you looked at the field at that moment, the electric field would have to be tangent to that field line, right? That would be the electric field at that moment. If you looked right here, you know the electric field would be this way. Okay? This isn't necessarily the path a particle would take, but the electric field is telling you this. And like I said before, the number of field lines is proportional to the size of the charge. The alpha is a proportional symbol to the size of the charge. Right? The direction of the E field is always tangent, so the actual vector itself is tangent to the lines. And the density of the lines can tell you then the strength of the E field as well. Indicates strength of the field. And again, it's always drawn with respect, is what they say, with respect to a positive, and they would call that test charge. And again, you're always drawing the lines like what would happen if it was a positive test charge. They might do something, so this is just a single charge, parallel plate, dipole, but you know, we wouldn't draw the whole electric field, but we could look at a situation on a grid where, let's say we had a charge here, a charge here, and a charge here. Let's say this is a positive guy, and that's a negative guy, and that's a positive guy. And let's say I wanted to find the electric field at that point in space right there. Again, what is this charge going to do? Well, this charge is going to push it. And how big? Well, there's the electric field, and you just tell me this charge and that distance, and then I can tell you the magnitude of the E field, and again, it's a vector. It's annoying, I know. This guy is going to push it up, and this guy is going to pull it this way. And so you'd have to find all those things. And so the total E field is, of course, the summation of all the individual E fields. So we would have to break it down into its components. We'd have to do an X hat and a Y hat, where if we said that was like E1, E2, E3, so this was like, I guess this was Q2, and this was some Q1, and this was Q3, then we would know the X direction would have to be some E1 cosine theta minus E3, right? This is to the right, but only a certain amount based on that angle, and we could find that angle if you knew those distances. And then E3 is to the left. And then upwise, we would have to do, what, E1 sine theta, and then plus E2, because they're both up. Again, I subtracted here because this is a right, and this is a left. And this is an up and an up. And so you would get some component, and we could figure out, you know, based on the size of the charges and these distances, how big these are. But let's just say that this one's a really big charge, so this one ends up being up and to the right more than this. And so then the electric field is just one vector. And so let's say that we had that there. And again, this was more right than this was, and it was both up. So if it was still a little bit to the right and way up, then our final electric field vector would be like this. He would have a certain magnitude, and it would be at a certain angle. Okay, it's just like adding up forces. Again, it's a vector, so the total summation is just the vector sum of those. And again, I understand these problems get a little tedious because you have a bunch of cosines and sines, especially if you have some distances. You know, this is some distance d vertically, and it's some distance L over here, and so you have to use d on L to find theta, and some of these are going to have L squared, some of them are d squared, some are going to have L squared plus d squared. But you can go through numerically and find it out. Again, it is a vector field, is the vector sum of all the individual vectors, and you know, we spent all fall in mechanics looking at vectors, so it really isn't that bad. Okay, so you can have static situations like this. You can have dipoles, single charges. You can look at an electric field. They could just give you a picture of an electric field and you can answer questions about it. Remember, positive charges always go with the arrows. A positive charge would go this way, where a negative charge actually go against electric fields, which are a little weird, but that's what a negative charge would do. We use parallel plate capacitors to get a uniform electric field, and then we can do all questions like this. Certainly we can't ask for anything here except that I give you a point in space and find electric field, and if I give you a different point in space, you'd have to do all these calculations again for that particular spot. Okay, this is in general how you're drawing them. The number of field lines coming from a charge should be proportional to charge. The electric field itself is always tangent to the field lines. It's not the path of the particle. It just tells you the direction of the force at that moment. The units of an electric field, remember, are newtons per coulomb. They tell you, if you put a 1 coulomb charge there, how many newtons it would feel. The density of the lines indicate the strength of the field. Hopefully you can see that the density of the lines are stronger, and as you get further and further away, they get less and less dense. Same thing here. Look at the density of the lines here versus if you went way out here, you might not even have any lines. And it's the electric field lines are always drawn with respect to what a positive test charge would do. Okay, hopefully this gets you kind of started on electric fields.